Started, and hopefully some students will join us. This week we're going to go over chapters 4 and 5. And chapter 4, you're going to learn about comparing groups, outliers, and time plots. So let's take a look. I've worked on this problem already. We're going to go into StatCrunch in a minute, but let's just take a look. This is a data set from chapter 4 called population growth. And I did a 5-number summary here. I have the min, Q1, the median, Q3, and the max. And then here's the histogram that accompanies the data. And this data set also included the region of the country. This was looking at percent change in population growth. And so I went ahead and I did a histogram for each region. So this was Southwest, and the other one I think is called the North or the Northeast. Southwest and then Northeast, Northwest. So if I look at these, and also here's the 5-number summaries for the 2 regions. This is interesting, but it's really kind of hard to visualize. If you notice, I did the same scaling on both graphs, but for this region here, the Northeast, Northwest, everything is kind of scrunched up down here like below 12. And if I look at the Southwest, there's a lot more variation in the data. So it'd be helpful to have a different way to look at this information. And the way to do that is using box plots. And if you remember, we learned about box plots in chapter 3. And it would be interesting to put the data on the same graph so we can really pictorially see things a little bit better. So what I'm going to do is compare by regions. I'm going to share the screen. It'll take a minute for it to come up. Show you the steps for creating the box plots to compare groups. All right, so let me find my StatCrunch. That's not it. Hold on, just bear with me. I've got a lot of windows open. So, Okay, let me go back here and trying to get it to collapse. There we go. So let's go to StatCrunch from the toolbar. And I want to go to data sets from the textbook. And this is in chapter 4. And it's called population growth. And what I'm going to do in here is go up to graph. So here's that information. I'm going to go to graph, and I'm going to do a box plot. And I'm going to select the variable percent change, the only one I have, and I'm going to group by region. And make sure also you click the use the fences to identify outliers. And then all the way at the bottom, select same X and Y axis. So you get the box plots on one graph. So here is the separated data. And let me also go ahead and graph the data combined. So let me go back and do a box plot for all the data without grouping. And let's go there and there. And again, I don't need to do this because I've only got one this time. So here's all the data together. And then here's the data when I separate it by region. And one interesting thing to notice is when I've got all the data together, I've actually got 2 outliers, but when I separate by region, I actually only have a single outlier. Now, let me pull this one over here and get this one in this side here, because I want to show you something you can do. We talked about this earlier, but if you take your mouse and highlight these 2, and then scroll down in the data set, it will highlight the 2 particular states where these are the outliers, and I'll tell you their value. So that might be interesting for you to know about. So what does it display? How does it compare the regional one by region compared to the overall one? You can really see a lot more of what's going on and on the same scaling. So let me go back to WizIQ and stop sharing. And I think it's really helpful because now if you look at this graph, it's a whole lot easier to compare the 2 regions than it was when we had the box plots. I'm sorry, the histograms. Let me just go back to the prior slide. Where I had the histograms. Nope, going the wrong way. Oh, here's the one I wanted. So remember when I had those histograms, it's not really very easy to compare the groups. You've kind of jumping from one graph to the other. But when I can go ahead and put the box plots on a single graph, it's really a nice way for you to compare groups. So to use box plots to compare groups, very, very helpful. You'll find this helpful in your investigative task for Unit 2 also. And again, this slide just shows you about identifying the outliers, which we just did. And again, you can find the one outlier. So notice when you separate them by region, suddenly there's only a single outlier. There's not two outliers. And here's another interesting graph. Again, these are box plots, and this time they're being plotted over time, and it's the month of the year. And this is a really interesting display. If you look at it, you can really visually follow your eye across. These are wind speeds in a particular region of the country, and there's a box plot for each month here. And you can really visually see that in the winter months, there's a lot more variation. Summer months have lower wind speeds. A lot of outliers down here at the end of the year. So a really nice display. Again, easy to compare the groups. Now that's the same data we just had on the other graph, and these are the individual daily values. And again, you see that same trending here. Middle of the year seems to have the lower speeds. Now, what do you do if you have outliers? If there are clear outliers in the data set, and you're going to report the mean and the standard deviation, you want to report them with and without the outliers. You can't just remove the outliers. Remember, the median and the IQR are not likely to be affected by outliers. So if you do have outliers, you may want to go with the median and the IQR. But if there's some reason you need to report the mean and the standard deviation in the presence of outliers, I would report the mean and standard deviation with and without the outliers. So what can go wrong when you're using this approach? So let's take a look at this graph here. You have to be really careful. If you're comparing groups that have a whole lot of different spread, if you notice here, this is the cotinine levels in, this is I think it's like no secondhand smoke, and this is with secondhand smoke, and this is an actual smoker. And if you notice for this group here, there's really very little variation when it's compared on the same scale as the smokers here, where there's a lot of variation. So this might not be a very helpful display. You could probably display these two side by side, but this one is really overwhelming the other two groups. Okay, let's look at a couple problems that you'll see in your homework. A company sells frozen pizza in 4 markets and wants to examine the prices that the stores charge for pizza slices. Here are box plots comparing the data from a sample of stores in each market. What are the two variables being compared? So one thing when you make a display or read a display, you want to make sure you understand the information. So we're looking at what? We're looking at pricing. And then along the x-axis here, we're looking at what? A sample of stores. So you want to keep in mind what it is that you're examining. Do the prices appear to be the same in all 4 markets? Okay, so let's take a look at the graphs here. If I look at the middle bar, which is the median for each group, it does not appear that this group appears to be different from the other groups. It appears to have a lower median. Let's look at the answers. No, the prices appear to be lower on average and more variable in city C. That sounds like a good answer. Appear to be higher on average and more variable in city D. Actually, no. Lower on average and less variable in A. They appear to be the same in all 4 markets. When you're reading a multiple choice question, make sure you read all the answers. And this first answer is the correct one. There's more variation here, and they appear to be lower. Did the presence of outliers affect your overall conclusion about the prices? We didn't really even look at the outliers, did we? I mean, this one does have a high outlier, but really when we were talking about the median or the mean price, we really didn't compare those. So we would say, no, it didn't really affect our overall conclusion. So sometimes even though there's outliers, you still can make conclusions about information. Okay, let's look at this graph here. This is called an ogive. It's a kind of interesting graph, and if you look at it, along this it's showing winners of a horse race, and they're winning speeds along the x-axis. And then along the y-axis it shows the percent of the data values below that number. And we can use this to find, first, the median. So remember the definition of the median is the data value such that 50% of the data are below it. So on this graph, if I look here at the 50% mark and I read over, it looks like it's about 35.8. Notice here again, 50% goes over to just about here, and it's almost 36, but not quite. So I put it about 35.8. How about the quartiles? Okay, so the first quartile, it's 25% of the data is less, so I go over here on the y-axis up to 25%, and that looks like it's about 34.5, and then Q3 is 75%, and that looks to be about 36.7, 36.8. Use the graph also to do the range. Okay, the range is the minimum maximum. Okay, so the minimum value here is just about 31. And the maximum, maybe 31.1, the maximum is about 37.7. So if I take those two values and I subtract it, I get the range, which is about 6.6, and that's in miles per hour. Okay, the IQR, if you remember from the prior slide, we had 36.8 and 34.4, Q3 and Q1. And if we subtract those, 50% of the winning speeds fall within a 2.3 range. Or another way to say it is 50% of the winning speeds fall between 34.5 and 36.8 miles per hour. So again, this graph is called an ogive, interesting display. Okay, here's a comparison across histograms of different classes of students and their scores on a particular test. And we have class 1, class 2, and class 3. Notice that the scaling on the x-axis is exactly the same. Scaling on the y-axis is a little tiny bit different. Let's take a look at a couple questions. Which class has the highest mean score? Highest mean score. Now remember, mean is the average of the data values. So for this class here, it's nice and unimodal and symmetric, so I know the mean must fall between 60 and 70 here. And on this class, about the same. But look at this class here. It's got, if you count up how many students there are, 1, 2, 4, 7, 11, 19, there's 25. I'm going to go ahead and jot that here because you might want to know that later. This one looks like it has 25 students. And then if I notice, 8 plus 15 of those students have scores above 80, which definitely means that the mean is going to be higher than the 60 that we see up here. So class 1 would have the actual highest mean score. Which one has the highest median score? Now again, remember on class 1, the median score here is going to be the 13th data value. Now, I know that 15 of them are up here, so the median must be between 80 and 90. Here, the median is going to be 60 to 70, same thing here. So class 1 also has the highest median score. For which class are the mean and the median most different? All right, let's look at class 2 again. The mean and the median are going to fall right in this middle bar here. Likewise for this class. It's actually going to be class 1 again. So even though they have the highest mean and median, they're also going to be the most different. Okay, let's stay with this problem again. For class 1, which one's going to be higher, the mean or the median? Now remember what we said when there's a skew. What does the skew do? The skew pulls. Skew pulls the mean in the direction of the skew. So the mean is going to be, let's look at the answers. The mean is going to be higher. No, the mean's going to be lower. The median's going to be higher since the distribution of scores is skewed to the left. That sounds good. The median is higher because the distribution is skewed to the right. No. The mean is higher. No, the right answer must be the second one. So even though they're both high, the mean's going to be pulled downward toward that skew. So it's going to be slightly lower than the median. Which class has the smallest standard deviation? All right, now, remember standard deviation is a measure of the distance of the data values from the mean. Now, we said in this class 1, the mean's going to be somewhere up here. So there's a lot of data values far away from it. So this is going to have a pretty big standard deviation. Look at class 3. Its mean is probably here between 60 and 70, and it's got a fair number on either end. However, and the same thing with this one, this is very nice and symmetric. This is actually going to have the smallest standard deviation. Class 1 is going to have the largest, or sorry, class 2 is going to have the smallest. We're talking about smallest standard deviation. This is going to have the smallest one because there are fewer data values, test scores, out here in the most extreme bars on the histogram. Which one has the smallest IQR? We can't be sure about this, but because it has a smaller standard deviation here, class 2 probably has the smallest IQR. So this is an interesting way for you to look at a graphical display to make some inferences, even though you don't know the mean, the median, the standard deviation. All right, one more with the box plot side by side. This is the age of people involved in accidents by their role in the accident. Which role has the smallest range of ages, and what is that range? Okay, so remember the range is the distance from the largest to the smallest, largest to smallest, so largest to smallest. And it certainly looks like it's the cyclist, doesn't it? And is it about 40 years? Let's see, this is about 10 up to, a little bit over than 50, so that's about 40 years. Which one has the largest IQR, and what is that IQR? Now remember, the IQR is the length of the box. And if we look at these three boxes, the pedestrians has the largest box. And what is it going to be? About, looks like it's about 40, 45 years. Which role generally, and the key word on this one is generally, involves the oldest people? So when I say generally, that's really talking about the mean or the median age. So even though the passenger group has a lot of outliers on this side, I would go with the pedestrians because it has a higher, 50% of them are more than 45 years old, which is greater than any other group here. So I would say generally the pedestrian group has the highest, or the oldest people. Okay, I'm going to move over now to chapter 5. And we're going to take a look at we're going to learn about the normal distribution, z-scores, and the empirical rule. So what is a z-score? Okay, the z-score is actually a standardized score, and we're actually measuring, it has no units, we're measuring the distance each data value is from the mean and standardizing it by the size of the standard deviation. And these are called z-scores. They don't have any units. The distance of each data value from the mean in standard deviation units. And we want to remember that a negative z-score tells us the data value is below the mean, and a positive z-score tells us the data value is above the mean. So here are some summary statistics for a small company payroll. And the question is, do you think this distribution is symmetric, skewed to the left, skewed to the right? Explain why. Okay, so where might we look for that? Let's look at the mean and the median. First thing we notice here is the mean is below the median. And what else might we think about? We could look at the distance from the mean or the median to the lowest salary and to the highest salary, 300 versus 550. But I think your key here might be this difference in the mean and the median that we talked about before. So it's probably skewed to the left because the mean is less than the median. And also if you went ahead and did your Q1, your Q3, and so forth, you would see that it's definitely skewed to the left. Between what two values is the middle 50% of the data? Okay, so they gave us here, they did tell us Q1. They didn't tell us Q3, but they told us the IQR, right? So we could use that information to find those values. So Q1 is 350. Q3 is going to be 600 plus 350, or 950. So 50% of the payroll values fall between $350 and $950. Okay, let's find a z-score. Cars currently sold in the United States have an average of 135 miles per hour, horsepower, with a standard deviation of 40. What's a z-score for a car with a 195 horsepower? Okay, so we're going to use our little formula. Z-score is the data value we're interested in, 195, minus the mean divided by the standard deviation. So this car is 1.5 standard deviations above the mean. That's how we interpret the z-score. Here's an opposite one. I give you the z-score, and I want you to interpret what it means in the data values for the given distribution. So people with z-scores greater than 2.5 on an IQ test are classified as geniuses. If the IQ test has a mean score of 100 and a standard deviation of 16, what is the score you need to be a genius? So we're going to work the formula the other way. We're going to take the mean, and we're going to add, because it's 2.5 above, 2.5 times the value of the standard deviation. So the genius IQ for this problem is 140. So when's a z-score really big? Okay, really big z-score tells us is an indication of how unusual the data value is. It tells us how far it is from the mean. The negative z-score tells us below the mean, positive above. The larger it is, positive or negative, the more unusual. And in just a minute, we'll have a rule to help you determine how unusual. Let's do a comparison here. We can compare things measured on different scales by converting to the standardized z-score. So an incoming freshman took her placement test in French and mathematics. In French, she had an 82, and in math, she had an 86. The overall results on the French had a mean of 72 and a standard deviation of 8, while the mean math score was 68 with a standard deviation of 12. On which exam did she do better compared to other freshmen? So the French z-score, she got an 82. The mean overall was 72, and the standard deviation was 8. So she scored 1.25 standard deviations above the mean for all students who took that test. And on the math, she had an 86. The mean score was 68 with a standard deviation of 12. So I put that into my formula, and on the math test, she was 1.5 standard deviations above the mean. So she scored better relatively on the math test than she did on the French test compared to all the other freshmen. And this is what we scale away. We take away the units here, and we put them all in standard deviation units or z-scores. So the normal model is an important model in statistics, okay? Bell-shaped curves, most people have heard of that. And they're used for distributions whose shapes are unimodal and roughly symmetric. And that's going to be an assumption we're going to check, and I'm going to talk to you about that in just a minute on how to check that. But there's a whole series of normal models depending on what the mean and the standard deviation are. And this is the shorthand that we use, capital N parenthesis, and then you would write in the value of the mean and the value of the standard deviation. And we use Greek letters now because this is referring to a population, and we're talking about parameters, not statistics. And we can do a z-score using a normal distribution. And here we're going to summarize it, calculate it rather, by subtracting the population mean and dividing by the population standard deviation. It's still called a z-score. And there's one important normal distribution called the standard normal distribution, which has a mean of 0 and a standard deviation of 1. And this is used frequently to refer things to. In a minute, I'll show you when we learn about the empirical rule. And we want to be careful because just because we standardize doesn't change the shape of the distribution. So we're going to want to check that assumption of underlying normality. And here it is here, the nearly normal. We can check it by a histogram or another data display called a probability plot. And I'll show you both of those in just a second. So here's the rule to help you kind of identify unusual data values. It's called the empirical rule. It turns out that in a normal model, about 68% of the data values fall within one standard deviation of the mean. About 95%, there's a 68, about 95% fall within 2 standard deviations, and 99.7, almost all the data falls within 3 standard deviations. So now we have a benchmark to compare standard deviations to, z-scores to. So if we did a problem and we got a z-score of 5, we would say that data value was pretty unusual because we know now that most of the data is going to be within or have a z-score of 3 or less. Okay, so let's take a couple problems here. Some IQ tests are standardized to a normal model with a mean of 100 and a standard deviation of 16. What is the z-score for a person with an IQ of 100? Okay, so how do we do z-score? Remember how we calculate z-score? We take the data value, 100, minus the mean, divide by the standard deviation. So when you have a z-score that falls at the mean, it's going to have a z-score of 0. Oops. What percent of people are expected to have z-scores above 116? Okay, so 116, I could actually go ahead and determine the z-score here for that. The z-score is going to be 116 minus 100 divided by 16, which comes out to be 1. So that's a z-score of 1. And now if I just go back real quick to my prior slide, where I had that little picture. So here's a z-score of 1 right here. Okay, and I know 68% of the data falls within 1 standard deviation, so how much must fall outside of it? 32%, and that's equally divided into the 2 tails, so 16% is going to fall above 116. We expect 95% of people to have z-scores between which 2 values? Okay, 95% within 2 standard deviations. So 1 standard deviation is 16, 2 standard deviations is what? 32. So we're going to go between 68 and 132. Okay, let's take a look at this problem. And then they're looking at a football league, and the number of yards gained by each of 154 wide receivers was recorded. Here's a histogram of the data. They give us the mean and the standard deviation. According to the normal model, what percent of receivers would you expect to gain fewer than 2 standard deviations below the mean? All right, below the mean. Now, if you remember, 95% are within 2 standard deviations, which leaves 5% for the 2 tails, evenly divided, so about 2.5% would be below 2 standard deviations under the mean. For this data, what does that mean? Okay, so let's go ahead and calculate. Let's take 487 and subtract 2 standard deviations. And what happens? We're actually going to get 487 times minus 2 times 331. We're going to get a negative number, which doesn't make any sense, does it? It says they should gain less than negative 175. So this model doesn't fit very well. And we can actually see that in the histogram. Remember, if it's going to be an underlining normal model, it should be unimodal and symmetric. So explain the problem with using the normal model. So again, if you look at that histogram, it's severely skewed to the right. So we really shouldn't be using the normal model. This data does not follow a normal model. Okay, this is a problem from the book, and I'm just going to put it up here because we're going to go to StatCrunch in a minute, but it's talking about cholesterol levels of adult American women can be described by a normal model with a mean of 188 and a standard deviation of 24. And the question they're asking you in the problem is, what percent of women do you expect to have a cholesterol level over 200 milligrams? Okay. And I'm just going to close up. I don't need this data, but what I do need is I'm going to go to Stat, and I want to go to Calculators, and I want to work with a normal calculator. All right, and so what I'm going to do in the normal calculator is I'm going to put in the mean they gave me in the problem, and they said the mean was 188, and the standard deviation was 24, and they wanted to know what percent of women would have a cholesterol above, so I'm going to make this a greater than, 200. And so here they give you a little picture here, and they show you, and here's the answer here, about a little bit less than 31%. And if you click over here on the 6895, it'll actually show you, which I think is a really nice feature. Here's the mean. Here's 1 standard deviation above, 2, 1 standard deviation below, 2 below. And then here's the number we want. About 30.8% or 30.9% of women would be expected to have a cholesterol above 200. And while I'm over here, let me do the next part of the problem. They want to know what percent of women do you expect to have a cholesterol between 150 and 170. And you have an option here called between. Notice when I change over here, it keeps the mean and the standard deviation, which is a nice feature. And we want to go between 150 and 170. And compute. Oh, typo. It's a pretty smart program. Told me I put it in backwards, 170. All right, so we expect about 17% of women to have a mean cholesterol between 150 and 170. And let me go back now to those. There's the first problem that we did, and then here's the second problem that we did with the between. Right there. Okay. And let's see, one other thing on here. Oh, the IQR. They want to do the IQR. So what I do for the IQR, let me go ahead and share the screen again. And I also want to show you one other thing while I'm in there. Okay. So the IQR. So what does the IQR mean? It means the lower 25%. So what I'm going to do now is I'm going to go back to the standard one, and I'm going to take out this value here. I'm going to go less than. I'm going to take this value out, and I'm going to put in here 0.25 because I want to find the area that corresponds to or divides the data into the lower 25% and the upper 70, and then we'll do this Q3 over here. So about 172, and then if I change this to 75%, I'll get Q3, which is about 204. So there's how you can do your quartiles. And then one last question. They wanted to know what were the highest 15% of women's cholesterol levels above. So again, I'm going to change this to a greater than. And I'm going to change this here, take out this number, because I'm searching for a value of the cholesterol that corresponds to the highest 15% of the women. So I put in the area 0.15, and so about 213 would be the cut point for the highest 15% of women's cholesterol values. All right, while I'm here, I just wanted to show you real quickly, you know how to do a histogram. I wanted to show you how to do a QQ plot, which is a normal probability plot, which is another way to check for normality. It's called a QQ plot. And this data set I have here only has one variable in it. Just pick the variable, and then it's going to create for you a normal probability plot, which talks about, shows you where you would expect the data values to fall if it followed a normal distribution. And we expect them to fall along a straight line. This particular data set does not appear that it does, and I think we know that. Let's go back and do a histogram. Because remember, we worked with this data set before, and it's not normal. And this is the way the probability plot looks when it's not normal. So you have two ways to check for underlying normality in a data set. And then to get the actual IQR, we have to do a subtraction. So for this data set, it's about 32. And then the last problem I did was finding the upper 15% of the women and their cholesterol values. And we just did that. It's about 213. So that's the material for today. Unfortunately, no students joined us, but hopefully this will help you as you're trying to work through your own problems for the homework this week. So have a great week, and hopefully I'll see you at our chat next week.